Okay, welcome everyone. Uh, oh, oh,
잘 안
right.
됩니다, 서 교수님.
Well, we have more than 100 folks registered for this KASSTA-KSEA joint. 안 돼요? Oh. How about now? Can you hear me?
Not good.
Not good?
Okay, it's good now.
뭔가
Yeah,
지금
you're kind of going in and out, but it's okay.
good now?
Yeah.
All right. Oh, I see. Let me then start again. Well, we have more than 100 folks registered for this KASSTA-KSEA joint webinar. So we expect to have more people to join, but it's time, so we're gonna get started. We are so honored to have these distinguished speakers today. I'm Eun-Suk Seo, professor of physics at the University of Maryland, and the president of KASSTA, that is Korean American Aerospace Science and Technology Association. I'll moderate this webinar today. First, KSA President, Professor Sohn, will give a brief welcome remark.
Thank you, Professor. I am, as a president of 52nd KSCA, Korean American Scientists and Engineers Association, and a proud member of Korean American Aerospace Science and Technology Association, KASSTA. It gives me a great pleasure to welcome you to the webinar today. We are kind of gathered here for the collaborative banner between KASSTA and KSCA, but we unite in our shared commitment to advancing aerospace science and technology, not only for the benefit of our respective nations, but for the betterment of humanity as a whole. Our organizations will stand as pillars of innovation, dedicated to fostering collaboration and promoting fellowships and nurturing the next generation of leaders in the field of space and aeronautics. KASSTA, I have checked this morning, much like KSA, but is a very noble mission. KASSTA strives to contribute to the social welfare and industrial development of both the United States and Korea through the promotion of space and aeronautics-related science and engineering. We seek to foster cooperation between the two nations in these critical fields and forging bonds that really transcends borders and propel us towards a brighter future. I would like to express my sincere gratitude to those who have made this event possible. Deepest appreciation goes to Professor Eun-Suk Seo, the president of, and the founder actually of KASSTA, whose dedication has been instrumental in shaping its vision and mission. I also wish to acknowledge the exemplary leadership of KASSTA Executive Director, Dr. Chun Young Park. Of course, I can't wait to hear from our speakers. I sincerely appreciate our esteemed presenters, Dr. Soyeon Yi and Dr. Tony Sohn, whose expertise and insights promise to enrich our minds and inspire all of us. Once again, welcome to the webinar, and let us unite in pursuit of innovation and discovery. Thank you.
Thank you very much. All right. It looks like our ED Park posted a chat message. Apparently there is some issue with Zoom link. I don't know what this is. ED Park, would you elaborate on what it is? What should we do about it?
I just got a message from our KASSTA room chat, and Eun Che, our editor, was trying to join, but she couldn't join because the Zoom link is no longer available for some reason. But oh, she just got in, so
Oh, okay. So it's resolved.
I just shared the updated Zoom link with through the Katok chat room, but I'm not so sure. Maybe some other members who received the original email may not be able to join, but I'm not so sure 100%.
Okay, so there was this confusion with the Zoom link. All right.
Possibly, yes.
Yeah, hopefully you can send out this new link to them.
Yeah,
To the
I did.
customer.
Okay, I'll double check with that.
Yeah. All right, so to continue now, our KSEA President-elect Professor O can give a few words.
Okay. Hello, everyone. I'm so excited to join the first webinar of KASSTA. First of all, I would like to share our signature, KASSEA signature conference coming up this August, UKC 2024, which had going to be happen in San Francisco. Our theme is the next era of science, technology, entrepreneurship with the artificial intelligence. And this UKC is somewhat different from before because of the location, Silicon Valley. We try to embrace many of the startup initiatives and industry participation. So behind of our theme, our focus is international collaboration with the Korea. So plenary session, we're gonna have a Thomas Stoffoff and the Future and Opportunity Symposium, which includes speaker from different areas of international collaboration and how to get the startups coming into the U.S. market. And I have included the tech talk, include the industry flavor, biopharma, and the IT tech session. So just give you a brief overview. Here is our speaker. We have a very capable speaker from the biopharma and the IT tech, and this is going to be a really interesting conference this year. Another things I would like to focus on, we have a lot of the program, and as you know, there will be a Wujuchong happening in the May in Korea. So we're going to have a special space session. This special session is co-organized with KASSTA, aimed to discuss U.S.-Korea collaboration in aerospace research. I have visited the KASSTA, and a number of other organizations related to space, and they will be participating in this session. And also JPL aims, there will be a speaker from NASA. So another thing is, because of the KASSTA initiative, I'm working with Professor Sohn to have an aerospace forum at the conference this year. This forum is a comprehensive platform encompassing every facet of space and aeronautic. As she said before, speaking with me, is that this is a multidisciplinary forum, not just the one area. So this is somewhat unique to our KSEA and also the KASSTA. And I will encourage you to come and participate at the UKC conference this year. And other than this forum, there are a lot of other activities. This year, I have included a demo session, not just the poster. And also another exciting event will be the combination of Beikei and Changbang and Southern Cal Group. They're going to have a special session as well. I hope you can join me UKC this year. And thanks for participating in this KASSTA webinar. Thank you.
Thank you very much, PO. All right. Maybe I should recognize our KASSTA officers. Vice President Yin, would you take 10 seconds to introduce yourself?
Yeah, can you hear me okay?
Yes.
Oh, okay. Hello, everyone. I'm Jung Bo-min. I go by JB In. I'm with Boeing Research and Technology based in Seattle. This is my great privilege to work with Professor Sohn to become the founding member of the KASSTA, and I'll be serving as a VP, and I would like to get to know you more. So glad to be here. Thanks.
Thank you. All right, Edie Park, 10 seconds.
Hi, my name is Chunyoung Park. I'm an aerospace engineer at Pyramid Space. I'm currently working on designing spacecraft parts and all the aerospace related engineering solutions. So nice to meet you guys all. Thank you.
Thank you. FDU. Or maybe we lost her. I thought I saw her earlier. All right. How about Daniel? Is Daniel Warren here with us now? He's the latest addition to us, Director of Strategic Partnership. All right. Maybe he will join later. All right. So let's get now started with the talks. So before we start, if you have any questions during the talk, use the chat box to write down a few words so that you can be in the queue, or raise your hand using the reaction button after the talk. We're gonna take and the talk. And when you asked, then at that time you can unmute yourself to start talking. Otherwise, please mute yourself. All right. Since the speakers' bios are available already on our webinar poster, I'm not going to go through all the details of the each speaker's bio, but first, let's welcome our first speaker, Dr. Soyeon Yi, the first astronaut of South Korea. I love her talk title. It's Mindfulness from Weightlessness. So let's give a round of applause. I'll do that representing everybody. All right, Dr. Yi, go ahead.
Okay, let me share the screen. And can you see the presentation?
Yes.
Okay. So nice to meet you. I'm so honored to be invited to this meaningful first webinar of this organization. And actually, yeah, today I will talk mainly about my space flight and experience before and after related with the flight. And then briefly talk about after career to get more opportunity to work together. And before starting, today is a quite meaningful day because, first of all, maybe some of you already know, and then today is the Day of Science in Korea, 과학의 날, and that is every year, April 21st. And so, first Korean astronaut program, when they opened the application, they opened the first application on the April 21st. And then on that day, I wrote my own application to apply for the astronaut selection program. So even I just celebrate that day with my own wine. So I just want to share that. And then there was the poster. I can see that when I applied for an astronaut on that day in April 2006. So we had a very interesting selection process, and this selection process is pretty much similar with many of the country who had a first astronaut of their nation, but a little bit different from the Russia and America and European Union, and then those Japan and those kind of country, because they have a periodic selection of an astronaut. So they have a little bit higher bar to have a prerequisite. But most of the country who has a just very first astronaut in their own country, they open to most of the general public in their own among their own citizens. So in 2006, we have a 36,000 applicant when they opened the application. So I was one of 36,206. I at that time, of course, if you see those number, and 1 out of 36,000 is less than a 0.1%. So as an engineer, it's not a good challenge actually, but I would love to make my wonderful memory almost the end of my PhD graduate school experience. But surprisingly, I got to survive out of the 36,000 to make the 245 during the first screening. And then October 2006, they made another screening to make the 30. And I thought that might be the end of my trial because I met all 30 people and they are incredible people. And I was sure that I cannot beat them. But luckily I got 10, and then we went to even Russia and had all kind of interesting experience in Russia to have a zero gravity and then hydro lab and skin scuba, kind of like that. And then 2006 Christmas Day, we had a final announcement who will be the first Korean astronaut candidate, final 2 candidate. And then on that day, I got a biggest Christmas gift ever in my life still, and became a final 2. And two of us went to the Russia and then had a 1-year training, not only with the simulator of the ISS, but also Soyuz capsule, and most toughest but meaningful and interesting training was the Russian language. You can see the top center, and I learned the Russian language with one of the Russian teacher who taught all the international astronaut around the 30-40 years. And then even if he cannot understand Korean or English at all except the Russian, but he read our mind because teaching the foreign astronaut for several 10 years. And it was really tough, but also interesting experience. And then also learn how to use the restroom in Soyuz capsule and in ISS, of course, because that is very essence of the life support. And also how to survive during the disaster, and then how to recording the camera, because we cannot bring all the cameraman and producer up to the space station, but we really have a huge responsibility to share all the experience and result to all their own citizens. And survival training, not only in Black Sea around the Ukraine area, but also in the middle of the forest for the landing on the ground. And then when we had some kind of situation, we needed to have survival training. And on that day is the April 8th of 2008. And then it was very surprising because I didn't notice about that, but very first female astronaut in the world, Valentina Tereshkova, came to the Baikonur spaceport. And then she escorted me to the launch pad from the bus. And then that was a really incredible experience. But I should explain a little bit more detail about on this photo, because some of my friends said, and then, are you really close friend with the first female astronaut in the world, Valentina Tereshkova? Because we doubt about it, because look at her face when she holds your arms, and then she doesn't smile at all. And actually, she was almost like my grandma during the training and even before and after my flight. But she really take me as a grandchild because my age was exactly same as her granddaughter. So she keep telling me everything will be okay, don't worry about it. Everything will be okay, don't worry about it, kind of like that. But I didn't worry at all, as you can see my smile. But as the grandma who needed to send their granddaughter to the space with on top of the missile rocket, and then she might have a smile at all. And on top of that, my mom was on the observatory in the 3 kilometer away of the launch pad, and then she fell down because it's her biggest explosion ever in her life, because she never saw the rocket launch. But it was even really successful launch, but for her, and the ground is shaking and it sounds is incredibly big, and then her daughter is gone away in the sky, so she just fell down, and then all the security agent and then urgent care peoples and medics, and then they should run to my mom to wake her up and take care of her. So as you can see, our Soyuz rocket and the Soyuz 12 rocket was going on really, really well. And then I arrived in a space, and then you can see kind of record video of my space experiment, and we planting the seed and then bring the fruit flies to check the whole their life in space, and some kind of body changing with the body fluid changing in the space. And also we have several Korean space fluid developed with the nuclear engineering research center and a fluid research center under the Korean government. And also we have a several chemistry and chemical engineering and physics experiment in space also. So not only as an astronaut, but also for the space experiment, they had really buying selection competition. They got more than 100 applicants for that. And then committee member picked only 18 experiment. And we have a significant and a very important experiment also I should bring up, and then to have performance like this is for the education for the students in school. So several of them got into the science textbook in Korea. So I'm so honored to that be covered on the textbook, not just the book, and it's a textbook and a national textbook. So we have 18 different kinds of experiment we brought up. And also, we should have a several cultural activity as the first Korean astronaut in the ISS. And also, as you remember, at the time, we had a Secretary General of UN was the Korean also, Ban Ki-moon. And then he shared one UN flag with me, and I brought up to the International Space Station, and then had some kind of hoping for the peaceful global situation. I'm so sorry and then sad that we had several war field still around the globe, but we really wish to have a peaceful Earth we could have. And then I put the stamp on that, and then that stamp is especially you can stamp on anything only in ISS, and then bring it back, and then bring to the New York headquarters of the UN. And then this flag is still exhibited right next to the UN Secretary General office on the hallway, so you can check it out if you go there. And of course, I shouldn't forget to have a fun, even if I have a really, really packed and a busy schedule in space. But you can see that I can find my inner peace in the middle of the air. And I had a third black belt in my taekwondo, but I've never tried a flying kick on the ground because of the gravity. Because for me, gravity is way too big to have a flying kick. But you can do even in the space station because there's no gravity. And many of the people asked the astronaut, and then I'm pretty sure that more than 99% of astronauts, they answered exactly same question. When was the best time ever during your space flight? And we all answered exactly same when we look down to the Earth. Because it's very interesting feeling if you look down to the Earth from the spaces, you can be the third person from the Earth. And then you feel like you are just get out of the some world, and then you can be the third person to all of the world around the globe, and then that's very interesting feeling. And also look down to the Earth, and you can recognize all the geographic, and you can recognize Italy and London and Bay Area, or some kind of African continent and some part of the North American continent. Some geographic shape is really unique. And then of course, as the first Korean astronaut, I really want to check it out, the Korean peninsula from the space. But as you can see, if you look down to the Korean peninsula at night, you can see like that. So top left corner, you can see the Seoul, Korea, and you can see the shape of the Hangang. And there's a lot of bridge around the Hangang. And if you have a really big, huge resolution of this photo, you can see the distinct border between the North Korea and South Korea, even if it looks South Korea is the upper area and then North Korea is down there. And you can see small little light leading, that's the Pyongyang. And except that's capital city, all around the North Korea is a total dark, even if it's not that in the middle of the night, because of their electricity grid is really weak, and then they don't have a 24/7 light in their own place. So especially the developed country and an underdeveloped country, they are neighbor each other. You can see the clear distinct border between two countries. So actually North Korea and South Korea border is very famous among the astronauts because they can see clearly. And second best clear distinct border is between the Mexico and US. And third one is Pakistan and India, because of a lot of the refugee tent, they are leading the light around the Indian border. So it's very sad if being famous is not always good, because those famous distinct border means really sad history of our country. And also, as you can see, we never ever choose where we were born at all. It's actually kids of your own, and then either they were born in Korea or they were born in US. They never choose it. And then kids on the North Korea also, and then kids in Afghanistan, kids in Ukraine, and then kids in any other country, they've never choose. But they have a totally different dramatic life depending on where you were born. So on that time, the reason why I put my title Mindfulness from Weightlessness is that was the quite eye-opening moment of my own when I looked down to the Korean peninsula from the space, because I've never thought all my environment and things are very helpful or grateful for me. I'm always easy to complain about that because some of my friends, they have a really well-off parents and it doesn't have to have a part-time at all and then focus on the study and then has a great resource to go around the globe and then even has a abroad trip during their high school or college or something. But I always busy to have on my part-time to pay my tuition and then dormitory and then kind of like that. So I always complain. But when I look down like that, and then what if the girl who were born this total dark area and they cannot even have a chance to get a scholarship or get a part-time at all, and then their life is totally different. And then even if girls or boys who is much smarter than me and they cannot have a life like I had. So from that time, yeah, I regret of my whole life complaining about everything I have. But now I got to know if you have any complaint about something, it means you have that thing. Yeah. If you don't have anything, you don't have anything to complain. And this is my last day of space station. Yeah, it's a kind of interesting culture, and then any country you were born, any country you are living, they always have a farewell party whenever they should say goodbye to each other. So we have a farewell party among the astronaut who will leave tomorrow, and then astronaut who will stay here for another next month, for 6 months. And because I'm the youngest, and they just asked me to sing, and they just clap the hands and sing, sing, sing. So I sang my favorite song and Fly Me to the Moon. The reason why I want to show off my singing capability, even if I didn't sing well, but I really want to show you that's the kind of normal life of the human, even if they are in a space, they have their own precious kind of life, and dinner together, and then coffee on the side, and then some religious paint on the back, they pray, and then a lot of the wires going around. You can see my laptop is on top of the ceiling, but there's no gravity. You can fly up and using your laptop, doesn't have to put on the table. And then some of the old kind of senior folks in Korea, how can you step on the table? But I never step on the table in the middle of the dinner, only because I was floating exactly same height of the table. So I'm just sitting, not sitting, but floating like that. And recently I feel really kind of old age of the space era, because for 50, 60 years, not only in Russia, but also in America, we had exactly same spaceship and same space capsule to go up to the orbit and then come down. So left side is the Soyuz rocket, and then Soyuz capsule is on top of the rocket, and then it's a nose faired under the kind of pencil shape. And it works for more than 50 years. So my Soyuz capsule is pretty much similar with the Soyuz capsule who flew to the space station 30 years ago or 40 years ago to the Mir. So I can talk with them commonly, and then I can kind of sympathize and empathize with all those 80, 90 years old cosmonauts and astronauts who fly to the ISS. But recent 10 years, we have a new space era. So SpaceX and Blue Origin, all different kinds of private space program comes up. So you can see that interiors and technology and everything's are totally kind of, yeah, disrupt. So even just the early 2000, we still using the stupid stick and then using all those kind of switch, and then only 50 hertz of the speed of the computer, and it works all because it's under the government and they don't want to change if it works well, and they don't have any innovation at all. But once the private space program comes up, they use the high tech for a space flight, and then it became much cheaper and very handy. And then that's a very interesting moment for me. So when the people talking about those new space, human space flight, and then I have no idea because I've never had a training with this spaceship. So that's a very interesting feeling, because among the 500 astronauts in the world for now, and I'm kind of a relatively younger astronaut, but I more have a comment with the old astronaut than the other younger astronauts. So that's interesting feeling. And before closing my talk, and I would love to share a little brief my career journey. So I studied my old engineering and technology kind of academic background is based in KAIST, because I did my undergrad and master's degree in mechanical engineering, and then moved to the biosystems department, and then graduate with the bio and brain engineering department because they changed their name in the middle of my PhD program, even if I've never done anything about brain. And from that time, at almost the end of my PhD program, I applied for an astronaut program, and then luckily got be chosen as a final 2 astronaut candidate and went to the Russia. And at the time, automatically I got hired by the KASSTA and then working as a senior researcher for several years until I left Korea. And I realized that I needed to add some more skills on top of my engineering and technology skill, because during I working in a career, I lose 5-6 years as my career track of R&D person. I've never had any research paper or never had any portfolio as an engineering PhD person. So it's hard to find my career path. So I decided to add MBA on top of that. And then from that time until now, of course, there's a small little cloud and a small little smokes between business development and MBA, because at the time, not only I left Korea, but also I left the California after my MBA degree. And thanks to my personal life huge changing to meet my husband and then move up to the Washington state. So didn't have any reference or networks at all. And it was really, really hard to be employed in American recruiting system. So 2-3 years, I was volunteered in a museum of flight and also teaching the physics 101 in a local community college, only because I need a job to do. And in the meantime, some of my friends introduced something and then find some good network and then people. So I started my business development career from the several different startups. So from the loft orbital, they are doing the Ubering of the satellite. So finding several client and then share the satellite together and then kind of this. And then I worked as a business development, especially in the Asian market and also Middle Eastern market. And then moved to the software company only because several executive members is my school high school alumni and science high school alumni, and then they invited me to work for them, especially for the American market. And then they developed the designing software and then prototyping software. So I connected with them to the Microsoft and Facebook and Google and all different kinds of Ford and Mercedes-Benz and then BMW, because that is very unique software for them. So working for them to grow their kind of business like a J-curve. And then I moved to the company called Nool, and they are developing the medical device, especially, yeah, it's very interesting. It's a Korean startup, but they developing the malaria diagnosis equipment to helping the African community and also LMIC country. And then I really feel attracted to the innovative technology, help the people in need. So helping them as a business development, not only taking care of the R&D and clinical research program in Noel in several different African countries, with working with Novartis and CDC and kind of like that, because they are finding the good drug for the malaria disease, and also working with several different American reference lab, because they really need the malaria diagnosis, because they keep having the malaria patient, even if not that many, but they needed to the control. So working like that, but still, I'm still looking for the more interesting and then challenging opportunity in the future. And before wrapping up my presentation for now, and I really want to introduce one of my favorite rocket scientists. He's Russian, and maybe some of you already know him, and then Konstantin Tsiolkovsky. He's the great-grandfather of the Russian rocket science, because even if he's never been a PhD program, just a local school teacher, but he got an idea about the multi-step of the rocket only can get out of the gravity field, and also making some conceptual design of the space station. So he said the planet is the cradle of humanity. One should not live in a cradle forever. And that inspired me a lot, because planet Earth is the cradle of all of us, because we got all we need from the Earth. But we should not live in a cradle forever, because whenever we try get out of the Earth, we have a great development of the technology. But it's applied for my own personal life, because whenever I left my comfort zone, I can develop myself and help other people more effectively, and in finding the new solution, because if you stay in your comfortable place, and then you cannot find any innovative ideas from there because it's way too comfortable. So that's my closing presentation always. And then thank you so much. And this is my wine label and then collaboration project with a Napa Korean winemaker. We are fundraising for the STEM Goals program in a Museum of Light. So if you are interested in, you can follow this QR code. Thank you very much.
Fantastic. Thank you. All right. Wonderful. Okay. So now this paper is open for question. Do we have anything? Oh, let's see. Any questions in chat? If not, let me see. Any hands up? You can use reaction button to raise your hand. Unjang Che, could you please go ahead?
Yes, can you hear me?
Yes.
Okay, great. Well, actually, one of the funny things is I'm the one with the person in the first round as the applied as the astronaut, the first candidate for the astronaut. So I'm surprised that I didn't know the exact, the amount, but it was kind of, the very competitive at the time. So the one of my question is there any reason why it's like to apply those kind of first astronaut in Korea?
Thank you for asking. Actually, many of the people wondering that if I ever dreamed to be an astronaut, even when I was a kid or something. But some of the people in this Zoom meeting and same kind of age or generation, we cannot even dare to dream to be an astronaut because when I was a kid, we didn't have even space agency and we cannot afford to have any space program in Korea. We even hard to feed our kids and family at the time. So I've never dreamed to be an astronaut. Even when I applied for an astronaut, I couldn't even dream to be an astronaut because it's way too far from me. But you know what? Frankly speaking, as a PhD student, I had a dream to do my postdoc period after my graduate in KAIST, really want to go to the US. And then we had a collaboration research with the UC Berkeley. And then that was my destination #1. And then having a good relationship with the several advisor in UC Berkeley also. But I realized that there's a crazy amount of the people, especially from the China and Japan, they have a perfect GPA score and a perfect TOEFL score and kind of like that, and how I can beat them to be recognized by the American professor. So when I look at that astronaut program kind of selection poster, what if I will survive until 300 or 30 people, then I will be the top 1% or less than 1% person. And then I knew that in America, and especially engineers in America, they love Star Trek and then Star Wars, and then they might be impressed by my astronaut selection program. So that was my little small excuse to apply for an astronaut, but it became much bigger than, and it turns out much bigger than I expect. But of course, it didn't mean I don't want to do. It means I cannot dare to dream about that. Yeah. Is it an answer for you?
Yeah, that's really good for me as well because I actually applied that too, and then I did not pass in the first round. So I really envy that at that time as a graduate student at that time. But yeah, thank you for
I'm
sharing.
pretty sure that not because you are unqualified, but because there's way too many people. So some people without having any reason, they can be screened. That's why I'm thinking I'm so lucky at the time.
Yeah, because the one of my hard part was a marathon actually. So I'm almost, I just entered the almost end of the the deadline. So that's the one of the reason. And thank you anyway.
Fantastic. All right. So Simon Sim and PO.
Okay. All right. Thank you for all sharing. Great story. I just have a few questions, but just I know you mentioned that 1 year training, but I think it's take place 2006. Do we need that much of really training? If I think next decade, do you expecting could be shorter for just someone that they wants to just visit? And how high aptitude actually can your experience did go?
Oh, okay.
The
Yeah.
distance. That is something that I'm curious about it.
First of all, they have a very well-developed training program for the foreign astronaut who only stayed for the 10 days in ISS. So frankly speaking, half of the training was the Russian language because you should communicate with the Russian language, and then it's hard to learn the certain language to have a technical communication and safety communication with their own people. So half of my training was the Russian. So at that time, I feel like, what if I can, I already fluent in Russian, then I don't have to waste this much of the time to translate or learn a language, kind of like that. So that's the big deal. And then another half is because I should have taken care of the space experiment, more than 18 different kinds, then I needed to understand at least basic power analogies. And then what if something happened, I should managing the risk and then managing the kind of thing. And also, just in case if something happened, even if I don't have to take care of all the risky thing and dangerous thing, and I don't know about any systems deep inside at all, but I should handle it. So I don't have to be intelligent to develop the laptop, but I should have enough intelligence to playing with the laptop to making some program. So that kind of thing. So flight participant who only for going there tour, like the Dennis Tito or Richard Garriott, and then those kind of rich people, they only take the 3-month training. And then those 3-month training is half of the Russian language, and another half is kind of like when you go up to the airplane, you have a brief safety briefing and introduction by the flight attendant. And for the space version is around a month, but they are crazy busy and rich people. So they just cut it several weeks and then come back and go. So it takes 3 months or 6 months. But some of the rich tourists, they really want to have a long training. Then they follow our training for a whole year. So it doesn't have to have a very long, but just in case they make those long journey. And then altitude and then height is, space station is rotating around the Earth 200 miles and then 400 kilometer above. It's a little higher and less because it's not exact circle, but that's kind of high. So it's not that far away. So from Seattle to the Portland or from Seoul and Busan, that's the kind of 400 kilometer. So kind of horizontally it's easy, but vertically it's that hard.
Thank you.
Welcome.
All right, great. So next is President-elect O.
Thank you for your talk. It was very, very interesting. Mike, I want you to look at the future of it. And as you know, UKC 2024 theme is AI. I know you talked about the tool that you were using was very, impractical. It's very difficult to use. But how would you envision that the AI will impact the space technology, mission control, all the thing you were doing, you have to do it manually, and now AI come into the picture. What do you think? Do you think the AI will be fully be able to, implement it into the space system, and they will make it a lot more efficient?
Oh, that's a really great question, because that's one of the question I always have in my mind. And then because very interesting observation also, because a lot of the new space startups and an era comes up, and a lot of folks to try to the blockchains and AIs and all digital technology in a space, but it's totally different from the non-human mission and a human mission. Because non-human mission, even if you failed, you just failed and you can try again. It's not a huge kind of impact on the people on the ground. But human mission is, even just one person is killed by any technology, it's a huge impact, not only on the industry, but also government. So that's very different. So as you can see, when you go to the long ship trip and then across the Pacific and across the Atlantic Ocean, they always have AI and some digital things and have a GPS and everything, but still they have a map with a paper, just in case. What if all the satellite doesn't work? What if all the digital things doesn't work? They needed to survive as a human. So they have old-fashioned technology, and they train the people to read the map and to follow those kind of directions. So human spaceflight might be the same, even if all the digital technology and AI help them really easy. and they don't have to use their brain that much, or they don't have to calculate that much, and that's really handy. But just in case, they should have a manual thing and a mechanical thing, because yeah, you try to open your car and then button locks, and sometimes your phone locks, but you always need a backup plan to mechanically open your car. So human space flight might has a little bit different aspect with the AI and digital technology, I guess.
Thank you.
All right, thank you. I have a request here. We need to take a photo. We are losing people, so we like to take photo first. And excuse us, Soyeon Yi, could you wait till the end of the second talk, and we can combine all the questions at the end of the second talk. Great, thank you. And there are many questions in the chat box, so Dr. Yi, if you could check chat box to answer there while we do this, and then we can pick up on, verbal questions at the end of the second talk. All right, so let's open your camera, and Dr. Let's see, where is our ED Park? ED Park, are you ready?
Yeah, I'm ready. Yeah.
Great.
So I'll take
Okay.
a picture. Okay, are you guys
All right.
ready?
Give us a cue.
Okay, I will. Okay, 3, 2, 1. Okay, just one more time. 3, 2, 1. Yeah, I take the picture. Yeah. Thank you.
All right, thank you very much. All right, so let's continue this second talk now. So our second speaker is Dr. Tony Sohn, who's the principal staff scientist at Space Telescope's Science Institute. And he will tell us about JWST today. All right, so let's give a round of applause. So go ahead.
Okay, thank you. I'll try to share my screen here. And I hope you can all see that. See, I'm in presentation mode.
Yep.
I'll try to take this thing away. Yeah, all right, there. So yeah, hi, I'm Tony Sohn from the Space Telescope Science Institute. I'm a principal staff scientist and in the JWST operations team. And before starting, I want to really thank the organizers and everyone here. It's a great honor to be one of the first 2 speakers for this webinar series, and I look forward to listening to the future ones too. Okay, so let me start with some quick facts about the JWST, James Webb Space Telescope. So it's a 6.5 meter telescope with a 18 segmented mirror. It has a focal length of about 130 meters. I'll talk about that a little bit later. Its weight is around 6.5 tons, and the size is about 20 meters by 14 meters. When I say that, it's the size of the sun shield, as you see here in the silver shape down here, and it has a size of around 20 meters in length and then 14 meters in width. That's about the size of a tennis court. So you can see how you can kind of compare how big that is. It's capable of detecting wavelengths starting from 0.6 microns to 28 microns. So it's basically, it detects a little bit of visible light, but mainly it detects near IR, near infrared to the mid infrared. So because of that, its operating temperature has to be extremely low, like around 50 kelvins or lower. That's about minus 223 Celsius. And of course, for that reason, this telescope is actually parked at the Sun-Earth Lagrange, the second Lagrangian point, which is about 1.5 times 10 to the 6 kilometers away from the Earth, which is, approximately it takes about 5 seconds with the light to go there. So going back and forth, it's going to take about 10 seconds. It has it has 4 different science instruments called NIRCam, NIRSpec, NIRIS, and then MIRI. So those are the 3 near IR instruments and then 1 mid-infrared instrument. And then the mission duration was originally predicted to be around like 10 years. So that was kind of a goal. But after the perfect rocket launch, now it's actually estimated to be about a little more than 20 years based on the fuel left on the spacecraft itself. And then the mission cost, of course, is about like $10 billion. You might have heard that this in many news media, but so that's why it's one of the flagship missions of NASA. Okay, it's a JWST mission is an international collaboration. NASA, of course, does the overall management, but the European Space Agency called ESA and then Canadian Space Agency called CSA also had their share. And then there's also these other companies that actually contributed to the project itself. For example, Northrop Grumman was the prime contractor that were responsible for the spacecraft and the sun shield. And also the integration of the whole system. There was Ball Aerospace and then Harris. There's also some universities like the University of Arizona that contribute to the project. And then the institute I'm working at called the Space Telescope Science Institute, that's the, we are a institute that actually operates the Hubble Space Telescope as well as the James Webb Space Telescope. So basically for the James Webb Space Telescope project, we are responsible for the science and the operations. And we also have the Mission Operations Center located on site, as you see here. And then among other things, we'll also do some flight operations and then software related things, data processing, data archiving. And another important thing our institute is responsible for is we actually provide the oversight of the science programs, meaning we do the proposal announcement. So like astronomers around the world propose for the use of JWST, and then we actually grade them and then distribute the number of projects for each of these astronomers after selecting them. All right. By large, JWST consists of 4 different parts, as you see here. The first one is the most important one, called the optical telescope element, or in short, OTE. That's the mirror part. And on the back side of the mirror, there's something called the ISIM, which is the Integrated Science Instrument Module. This is where all the science instruments are installed, like detectors, camera detectors, or spectrographs, and those kind of things. And then there's a sun shield, which I said is about the size of the tennis court. And then at the bottom, there's the spacecraft bus, which actually includes a lot of things like the antenna and also the star trackers and other things for moving the telescope around. So in this talk, since I work in the wavefront team or the telescope team, I'm going to actually focus on some things about the OTE, the optical telescope element. And first thing is that when the light from the distant universe comes through the telescope, it actually reflects on the primary mirror and then to the secondary mirror, and then it goes inside and then reflects twice. It bounces around further to get into the backside of the telescope. And then on the backside, as you saw before, there's the ISIM, which includes 4 different instruments: the MIRI, NIRCam, NIRIS, and NIRSPEC. And for each of these instruments, the light bounces around inside those instruments a lot more. So by the time it actually reaches the focal point, focal plane, the total focal length is about 131 meters. So it's a very long distance to actually travel. Okay, so most of you know that the JWST was launched on the December 25th of 2021. So it's about 2.5 years ago. That's the far left picture is actually the picture from the launch day. And on the top part, like that the telescope was actually folded into that a rectangular box kind of shape. And it was stowed inside the payload. And then exactly after the 3 minutes and 26 seconds after the launch, there was a fairing separation, which revealed the telescope like that. And then after that, for about a month, it actually traveled to the the second Lagrange point. That's the final destination. And along the way, there were many things that were deployed, as you see in this animation here. So right now you're seeing the sun shield being deployed from the folded configuration. And after that, it gets tensioned like that. And then the secondary mirror gets deployed. And then the wings of the primary mirrors get deployed like that. So right now, this is what the JWST should look like at the L2 point, and it's going to stay like that forever from now. All right, so right after reaching the L2 point, the second Lagrange point, the telescope actually was not aligned. The mirrors are kind of like all in a mess because of the launch. You know, there's a lot of vibration going on, so the mirrors get all messed up. So you know, when the light comes into the telescope and reflects from the mirror, this is what it's going to look like on the left. So you know, each mirror. So it's basically you know, simple way of saying this is it's going to look like a telescope that has 18 different mirrors pointing at different directions. So 18 different telescope basically. Now the goal of what we call the mirror alignment is to make this aligned like that. So all the mirrors are now pointing into so we're collecting the light, all the reflected light into one point so that it gets like the star gets focused into a point. So that's kind of final goal of what we call is the mirror alignment. And to make this possible, each of the mirror segment on the back has a device like this. So there's some actuators and then whipples and then some bars that looks like this. So, and then it makes it possible to tilt the individual mirrors and then rotate it around and also move around X and Y directions. And then there's also something called the ROC, the radius of curvature motion, which basically makes the mirror segments flatter or rounder individually. All right, so this is what we get when we image the telescope when we were on the L2 point for the first time. So this is actually just one star. It's not like 18 different stars. It's one star, and when we image this star, we get 18 different points for that star because you know I just showed you that, you know, the telescope is not, the individual mirror segments are not aligned, so they're going to pointing in different directions. The first thing to do is to actually identify which segment belongs to which source in this image here. So what we do is, for example, as an example shown here, we move around the B5 mirror segment, and we know that this is moving, you know, left and right. So that's why we tag this source to be B5. And then we do this for all the sources, and we know that you know which source corresponds to which mirror segment. So this is called the segment identification. So this was the first stage, and then once we do that, we make this into a nicely shaped, pretty shape that resembles the mirror, the 18 segmented mirror of a JWST, the honeycomb shape. And then after that, there's a slew of process that actually happens, but I'm just going to walk you through this animation because I don't want to go into the too much technical details. But basically what we do is we first focus each and every mirror segment like that, and then we have a good focus there. And then now what we do is we collect all the points to a single point. So we want to, this is called the image stacking. So we stack each star into on top of each other. Now the telescope is not, it still acts as a telescope that has 18 different mirrors because they're not phased yet. So the next process, we go through something called a coarse phasing. So this is basically trying to level each of the mirror segments that are adjacent to each other by using some interference patterns. And then also after that, we go through a stage called fine phasing, which actually phases the light reflected off of each of these mirrors and collect into a single mirror. Now, after this process, the 18 segmented mirror acts as a single 6.5 meter giant mirror. So that's kind of like what we go through after doing the mirror alignment process. And this is the result of the telescope, the mirror alignment. So this is an evaluation image. Many of you may have seen this image. Now, one thing to note is that the star was used to test how well the mirror was aligned, but we were kind of shocked. We didn't expect to see so many galaxies in the background. So these are all galaxies, each of them having like 10 billion stars, just like our galaxy, right? And they're like in the distant universe. Now, it's kind of like everyone was kind of shocked to see so many of these galaxies around, because like the telescope was working so much better than expected. So the mirror alignment was completed on April 22nd, 2022, and we celebrated by taking a snap in front of the institute, and also some of us actually baked some cake and we ate some cake of it. All right, so to quantify how well the mirror alignment is done, we use a metric called wavefront error, and as shown here, this actually measures how far the aligned mirror is from a perfect parabola. So it kind of measures, how far off it's from the perfect parabola in an RMS sense. So if it's closer to 0, that means it's closer to a perfect parabola. But if the numbers are higher, that means like the telescope is like on the right here. So it's like all the mirrors are not aligned and on a smooth surface. Now for JWST, what's important is that the biggest contribution to this wavefront error is actually the misalignment between the 18 different segments. The individual mirrors have a very small wavefront error. They're very close to a perfect parabola, or circular in this case, but the entire the parabolic area will depend on how well we actually level these different 18 mirror segments. And this is actually, this kind of summarizes how well the mirror was aligned here. Now, the right part is actually a collection of different elements of the contribution, elements that contribute to the wavefront error. But all you need to do is like just focus on the red box here. Now, of course, for the wavefront error, the smaller is better. The requirement was that the telescope has to be on around 150 nanometers in order to observe the infrared light that the JWST wants to detect. But after ground testing, after the integration of the telescope itself, the prediction was around 125 nanometers. But in the end, we actually measured it to be around the 80 nanometers. So it was much better than the requirement or the predicted values of the wavefront errors. And when you hear from the news media or some press release that the telescope is performing way better than expected, this is what they're actually talking about. It was the wavefront errors, the telescope wavefront errors was much smaller than what we actually have predicted. Now, unfortunately, the telescope doesn't stay still. Sometimes it moves around. It's a moving part, right? So the mirror segments actually they kind of like move around. They don't stay still. So sometimes what happens is this shows the wavefront error as a function of time, and we measure this every 2 days to see how stable it goes. And you can see that it's going up a little, and then suddenly it jumps up. Now these are kind of called the tilt events. We call them the tilt event because this is a result. For example, like for this one here, this is the result of one of this is actually the before and after picture, the phase map of these the 18 mirror segments and the difference here on the far right. And you can see that for this one mirror segment here, it actually made a tilt. It actually moved a lot in one direction. So what we do in this case is we send the mirror correction to compensate for these tilt events. So you can see that these arrows, the green arrows down here, that points down here, is every time we made a correction to bring down the wavefront error back to the bottom level of around below 70 nanometers. So we do that on a regular basis. We've been doing that for the past 2.5 years, and we kind of have a feel that how many times this happens in a year, a month, or a year now, and then we know very well how to correct them. So we can maintain the telescope in a very good state. Okay, so I have some images to show. I don't know how much time I have left. I can't see the clock now, but I'll try to go through this very quickly because, like, what kind of a talk without like pretty pictures, right? So I will start with the pretty obvious, the solar system planets, starting from Jupiter, Saturn, Uranus, and Neptune. So all of them, you're probably familiar with the pictures taken by the Voyager 2, Voyager 1, and also the Hubble Space Telescope. But these are kind of like in a kind of new way of viewing them because we're looking at the infrared. For example, with the Jupiter, we're seeing the atmosphere in more detail. Because we have a larger telescope, and we're also seeing the infrared. And the Saturn also shows a very bright ring. On the other hand, the planet itself is kind of dark. And Uranus, this is a face on a ring, and you can see the incredible details on these different, like the rings. I can actually count 1, 2, 3, 4, 5, at least 5 rings that are seen around the Uranus. And Neptune also looks like kind of a transparent kind of thing because it has a lot of methane gas that absorbs these infrared light. So that's why it looks like a kind of transparent orb or something. So that's the solar system objects. Now, James Webb also observed a star called Fomalhaut, and that's in a distance of about 25 light years. And what's incredible about this is that we're able to kind of resolve all these details about. So the stars is supposed to be positioned here. It's saturated. It's too bright to be detected by the detector. So it's kind of, that's why it's kind of black. That's artificial. But you can see like this the disk around it, and then all these ring. So inner ring, outer ring. All of these are kind of analogs to the asteroid belts that's orbiting around Mars and Jupiter, orbiting between Mars and Jupiter. That's analog to those, and we can actually see these in the 25 light years away with James Webb Space Telescope. And we can even see some overdensities here, which seem to be related to ongoing planet formation. This is a very young star, so planetary systems are currently being born. Another amazing image, this is kind of my favorite, obviously, and it's called the protostar in the dark cloud L1527 at a distance of about 460 light years. And what's happening here is that, so like when a dark cloud collapses, it starts to make, by gravity, it starts to make this like a disc-like shape, and then the jets come out in the bipolar direction, like up and down. So the star itself is like kind of hidden behind this dark band shown in the arrow here, but like the jets coming out from them are making these like filament shapes. And then the dark cloud actually has a different kind of density. The denser part looks as orange, while the less dense part like looks in blues. That's why it's kind of makes a very nice like the shade from like the orange to blue as you go from top to down. And then also a very famous object called Pillars of Creation. It's at a distance of around 5,700 light years. It's a star-forming region. Stars are being born down here. It's blowing all the dust and gas up toward the upper left direction. That's why you see these pillars. And at the end of these regions, there are also stars being born. That's why you see this very glowing lights. But it's kind of like interesting if you see, in that's the same objects in different wavelengths. Here I'm showing on the left, this is the Hubble Space Telescope image. That's the visible wavelength, about 0.5 to 0.7 microns. And you can see that the stars are, pretty much hidden. You only see the dust in front of these things. But once you go to the near IR, 0.9 to 4.7 microns, you see all the stars in the background because the infrared is able to see through the dust because its ability to detect the longer wavelength, right? So you see all these dust. But when you move to a longer wavelength here, this is also taken with the James Webb Space Telescope with the MIRI, called the mid-infrared instrument. So now we're at a longer wavelength 7.7 to 50 microns. Now the stellar lights, the stars are not bright anymore because the stars are only bright up to the near infrared, but it gets like fainter when you go to the longer wavelength. But what you can see here is like you can now start to see the very cold dust. So these are cold dust like as opposed to the warmer dust as you see on the right. So these are dust you see, and you can also make out some interesting. I kind of like this kind of looks like a space wolf to me. I kind of pointed out. No, some people agree, some some others don't. But yeah, overall it looks pretty. So this was actually featured as a Halloween picture, the left one, because it looks a little bit spooky. So we kind of announced it around like the Halloween. All right, I think I have like one or two more slides now. So this is Cassiopeia A. When a supernova explodes, what happens is like it leaves. So the core of the star actually is disappears, but visually you can't see the core of the star, but the outer shell actually expands to make these amazing shapes. So this is the aftermath of a supernova explosion that happened around 360 years ago or something like that. So again, I want to name this like a space dragon. It looks like a dragon to me, like the face here, and then like it's kind of like rolled up. But the left one shows the near infrared image, while the right one shows the mid infrared image. And it's kind of striking to see the difference of how they kind of trace the different kind of details. The left one shows a lot of stars again, but the right one does not. On the other end, the outer gas has more details on the right. So yeah, it's kind of like fun to see these the same images taken in the different wavelengths like this. All right, now we move out to the further distance to 24 to 60 million light years. Now this is again like the same galaxies shown in the visible light taken with HST, and then the near IR plus the mid IR taken with JWST, and you can just see that how the same galaxies can look different in different pass bands, like wavelengths. There's one thing to note is that you might see on for the JWST images, you might see these holes around here, like some of these like holes on the along the arms. Those are because of the supernova explosions. They actually make these holes once they this is a very active region of like forming stars. So there's going to be a lot of massive stars that are going off and like exploding as supernovae, and they actually make these holes like this. And it's easier to see in the JWST IR images than the visible HST images here. All right, so last picture. Again, this is also one of my favorite pictures. It's something called the super galaxy cluster 0416. It's around at a distance of around like 4 billion light years. And what's happening here is that the yellow sources you see here is the actual galaxy from the galaxy cluster. But what's more important is that you see all these sources that are kind of look very stretched and deformed. This one too here. Those are because of the what's called the gravitational lensing. So there's a lot of galaxies in the background, very far away in the universe, more than like 12 billion light years away. Now, as they go through through this like the foreground super galaxy cluster, the lights get actually bent and enhanced to make these kind of features. It's interesting to like these sources are actually sometimes the lens acts in a funny way that the same galaxy gets imaged like twice or even more times. Like this galaxy here is the same one as this one. This one is the same as like here. So yeah, so we're seeing. So I like this picture because it tells a history of it tells the cosmic history of the universe. It's like we're seeing lights that are coming from like 4 billion light years all the way to like 12 billion light years and more. Okay, so I wish I had more time to show you like more beautiful pictures, but I'll stop here and take questions if any of you have them. Thank you.
Fantastic. Thank you. All right. Okay, so any questions for Tony now? So I have to agree with your naming. All right, Simon Shim, go ahead.
All right, thank you very much. I'm really, really enjoying this James Webb Telescope, and it's just opening the new world and universe. So thank you, Tony. Just one question is, okay, you've been investing almost $10 billion for this telescope. Maybe two questions. But is there any other telescope plan that things we are maybe, because this machine can last, I don't know how long, what will be the lifespan? And that is something I'm interested. And also, now since machine is there, probably most of people actually focusing on the maintaining running this. Is it something that are we kind of accepting some recommendation, or everyone has their own interest to see, right?
Yes, that's right.
Yeah, so I don't know how that works these days.
So to answer the second question first, so we have a proposal system in the sense that anyone interested in using the telescope, they actually submit the proposal. This proposal cycles go every year, and then usually the rate, the competition rate is around like 14 or 15 to 1. So it's a very it's very competitive, and so STScI is actually responsible for taking all those proposals, and then we send them out to the experts in the field, and then you have a kind of a system for grading those, and then the top ones actually get the time to observe. And the answer to the first question is that yes, there are other giant like this. This is a flagship mission for NASA. The next flagship mission is probably going to be something called the Habitable World Observatory. And as you can make it from the name, the main purpose is going to be to detect and characterize the planets around the sun that actually has these planets just like Earth. So they might be able to like harbor life or something. So that's kind of like being it's not a firm plan, but the estimate right now is it's probably going to be launched around 2040 or 2045. JWST has a lifespan will have a lifespan of around 20 years or more. So hopefully, we kind of like we get to keep that telescope until the next one actually launches.
Thank you.
Great. So let's see. Daniel, would you like to open your mic to ask a question, since you say you cannot raise your hand? And after that, Soyeon Yi can. Let's see.
Oh, yeah. One of the questions that I had for Tony to start with was, so what were the factors that contributed to the predicted values versus the actual values on the performance of the antenna?
You mean the telescope, right?
Yes, sir. Yeah, the telescope.
Yeah. So yeah. So when you actually make the prediction, you actually put a lot of like budgets. You actually make room for a lot of these errors. So like make predictions that there's going to be some error budgets on this side and that side, and once you pile that up, you get to the number of like 125 nanometers or something. So that's how the prediction was set, and then so I guess like the fact that we're actually much better than that, like maybe twice as better than the requirement, is because we nailed all of these like different elements to the absolute lowest value as we can. So we, of course, like the engineers knew that we can actually reach this the 75 or like a little bit higher the Wayford error. But of course, when you make the predictions, you want to be a little bit more conservative and realistic, and that's what with this the middle arrow was. But it ended up like everything. I guess like the stars aligned. I would say the stars aligned to make everything I guess like close to perfect, and that's why we have a very nice telescope like that performs much better than predicted. Yeah.
Great, thank you.
All right, wonderful. So Soyeon Yi.
Yeah, thank you for a wonderful presentation. I'm always excited to see the Hubble telescope photos and then James Webb photo, and they're always excited. And then I'm wondering about that, and even if we just side by side compare you have former photos and recent photo, or Hubble photos and then James Webb photo, and then a little bit different colors, and even if the shape is same, so I guess like it might be depending on how to transform the signal, so we cannot know how it exactly shows like that when let's say if we can go there several millions light years and then close to them, and if we can see the bare eyes, and then maybe it doesn't look like that, because when I was in space station and then I can see the stars and it's totally different color than when I look up the night sky because of atmospheres and the filters and kind of like that.
Right.
So if I saw that, and then what if I can go there, and then is it really look like that?
So that's a very good question and very good point, because now just for as an example, if you comparing these two pictures, on the left is a visible wavelength, and they actually map the colors close to what it should look like in real color. So for example, like 0.6 micron would be somewhere around green, 0.5 would be somewhere around blue, and the 0.7 would be like yellowish red. So that's how it mapped it. So I think if you can get closer one day to this nebula, then you'll see something like this. On the other hand, for the James Webb Space Telescope, what we actually did was that, infrared, human eye cannot detect infrared, right? So what we did was we tried to translate as close as possible, keeping the principle from the visible light, the wavelength, in the sense that, longer within the near infrared, for example, here, the shortest wavelength, 0.9 micron, would be mapped to like something like purple, and then 1 point something would be mapped to like a blue, and then on the other extreme, 4.7 micron would be mapped to a red color. So that's how we kind of like assign different colors, and then combine the color the images to make something that. So I would say it's not. Some people say it's like fake. I don't like to use that word, but I would say it's a kind of a pseudo color. What it would look like if the human had ability to detect infrared and make it into colors. So that's kind of a way to, yeah.
And even map the light, even human cannot recognize it. So maybe some other animals, they can see like this.
Right. Yeah, exactly. Yeah, I would say that. Yeah. If there's an alien that can see like longer wavelength than humans, then they would probably see something like this.
Yeah, thank you. Because when we saw the first black hole picture, I was so disappointed because it's not look like that. If we go there and then see that, it's just a mapping and transform.
Right.
Pretty much like that, right? Yeah.
Mhm.
Thank you.
Great. All right. Are there any more questions? Did I miss anyone? Hand is not up, but Kenny Park, do you have a question? Your microphone is open.
Yeah, can you hear me? I have a question. When the
Yes.
JWST was launched, there was a lot of media coverage on the validity of the Big Bang theory. Somehow the JWST revealed that our cosmology understanding may be revised. And there was a lot of coverage last year or two, but recently I haven't heard those speculation was died down. And what's the current state of the cosmology revision kind of speculation?
Yeah, so good question. So I would say, like, in short, it was very exaggerated, because like there were some things that the cosmologists did not expect. For example, there were more higher number of massive galaxies that were kind of detected in the very early universe than expected. But it was still within what could be predicted by the cosmological simulations. But I think that in that sense, the press was kind of exaggerating that, the JWST. I also saw a lot of like news headlines saying JWST breaks the cosmology, or broke the cosmology, or whatever. But I think those were kind of exaggerated. Now I think anyone actually using JWST that works on these galaxy theory, formation theories, or the cosmology kind of agrees that, you know, these are not outside the parameters we can cover. They're definitely within the parameters we can cover, but there are, if you go to the details, there are things that surprise. There are a little bit surprising. Not, I wouldn't say like unexpected, but it's a little bit surprising because, you know, we still need to make the models, cosmological models, better to produce these things, as I said, like some more massive galaxies found in the early universe. So that's, yeah, that's kind of my, by the way, I'm not an expert on like cosmology or anything, so I can't like talk about the details, but so I just like I talk to like cosmologists and galaxy formation theory, like people who do simulations, and that's what people tell me basically. So
Okay, so those initial controversy has died down, and so the basic hypothesis on the Big Bang theory still holds, according
yes,
to you?
yes, yeah. Big Bang. I don't think Big Bang theory itself was ever challenged. That was also a little bit kind of exaggerated. Some people who try to, you know, make things a little bit voice out things. They wanted to actually make a little bit more exaggerated statements. So
Okay. Yeah, I was hoping that NASA will make some definitive announcement that the validity of the Big Bang theory holding their scientific merit. In the beginning, last year or two, there was so many media coverage doubting our understanding cosmology. I was a little confused.
I see. Okay.
I
So,
think
okay.
that's about inflation. So it's a slight modification of a Big Bang theory. It's not that you abandon Big Bang theory, but rather elaborated or advanced now. I would say, we know better with this better telescope.
Okay, so anyway, that clears some of my doubtings. Somehow, well, if you like me, I was a little confused watching a lot of media coverage doubting cosmology and so on. So I'm not in that field, but as an average citizen, I was really confused. I was hoping the NASA will make some official comment or clarification. Where do they stand with the Big Bang theory? But anyway, you helped me a little bit more. So there was a lot of speculation, erroneous assumption, a lot of famous physicists making those kind of things on the media.
Mm.
I mean, I don't know whether that was, I think right now I don't see those kind of video coverage floating around. So according to what I heard today from you, those speculation died down.
Yes.
Okay, good,
I
good.
suggest we discuss this separately and move on to another topic. All right? Yeah.
Okay, thank you.
Sure, thanks. All right, so Chang Ro is waiting with her hands up. So go ahead.
Yes, I want to add about infrared emission. So in this pillars of creation, you can see the background is really bright. So you can see dark cloud, in reflection. But however, real infrared lights, you can see kind of heat sensor. There are a lot of infrared goggles. The military especially, you sense the enemy is passing through while the light, optical lights cannot see. So, this case, you kind of see the same shape, but if you see like Orion, constellation, we see only stars. But actually, if you see the infrared, there are so many clouds between the stars. So if you just look at the stars, like, Star Wars or those shows, you will see, the spaceship goes through between the stars is so empty, but actually infrared lights the other infrared pictures show that the space is really filled up a lot of clouds. That's basic difference in infrared light. So maybe if we go out see in the space, we need to put in the infrared goggles.
Right. Thank you. Thank you for the clarification.
Also, can you comment on the follow-on? I saw somewhere maybe NASA or some other organization is already starting even bigger telescope, bigger than JWST.
Yes, yes, that's true. That's so it's not in a firm design state yet, but like there's an initial study going on with so I already commented about that, but there's something called the Habitable World Observatory, which will probably be much larger than JWST at least.
Okay, when
Yes.
that will be?
So
when-
the current target launch date is around 2045, 2040 to 2045, so maybe like 20 years later.
Okay. Okay, so that's good. So NASA has a budget already allocated to do some basic research.
For this, yeah, some budget for the basic research, but not the telescope itself, because they don't know if they're gonna go with the plan firmly yet. So it has to go into like several steps of reviews, especially the mission critical review. Like, but they're on the study right now.
Okay, good. All right, thank you.
All right. So earlier we had Sohn Lee, who I deferred the question to Soyeon Yi. Was it resolved in chat or?
Yeah, I asked through the chat and then I got the response. Thank you again.
All right. Do we have any other questions to either of our speakers?
Oh, I have one, just engineering questions, if you
Okay.
don't mind. Yeah, basically this is hexagon, right? I'm
Right.
practicing structure engineer. So somehow I heard some story, but do you happen to know any background why they chose hexagon and why 18 lenses?
So hexagon is because it's very simple. If you don't have to like think very complicated. Hexagon is because they wanted a shape that is as close as possible to a circle, but that can actually fill the space when you actually like stitch it together. So if you think about it, it's like it's going to be either triangle or hexagon or some things like that. Of course, hexagon is the easiest to make out of those, and it's going to be most stable. It's going to be more stable than the triangle, obviously. And then there's also some things to consider, such as like diffraction spikes, because at the end, when the light actually like reflects, there's going to the edges are going to actually cause the diffraction spikes. So you want to minimize that. So you want to actually make the shape as close to the circle as possible. So that's why they chose the hexagon. Yeah.
Maybe similar, because this is what I heard, that the NASA had a hard time to choose. Initially, they choose circle, right? But
Right,
thing
that's right, yeah.
is, one thing from our end, they need to figure out how to fold it.
Right, that's right. Yeah,
Because
that's
they need
another.
to put it in
right.
the rocket. So they chose, they hired origami specialist. Origami specialist, that's what I heard. So they kind of choose the hexagon and just figure out how to fold it and unfold it.
Right.
Thank you.
All right. So I think it's time for us to wrap up now.
Okay, well, another question. I don't know. I assume that your background is somehow physics related. Are there any enough talent being ingrown in US to address this kind of coming space exploration? Are there enough people? Are we bringing enough young people into this field to make much more progress? I'm just wondering that whether young people are motivated to study in this field and enough funds available to push forward. Can you comment? I don't know whether do we have enough? Do we have in US enough talent being grown to address the coming challenges in space?
I mean, assuming that question was for me, I think the answer is yes, because if you take the James Webb Space Telescope as an example, there are many young people actually who are involved in working on that. So my background is astronomy, by the way, and there are astronomers, engineers, physicists, all like IT specialists, all sorts of people that contribute to the project, and there's a very high fraction of young people that actually were interested in getting on board to the project. And so in terms of the interest itself, I would say it's the prospect is very good. I think the budget is also very good in the sense that NASA is like right now, there's no plan to actually dial down the budget for the JWST. They're only like increasing every year. So yeah, the prospects look very good for space space telescope missions, at least.
Yeah, good to hear. So if you are you if
Kenneth Park, would you please now wait a little bit? We need to wrap up so that other people can leave because we are overrunning the time. You can have private questions also separately. Thank you.
Can I just have one question? So there are many questions in the chat. Is someone going to like copy and paste it to me? Because I like to answer them. I know if we close Zoom, it's going to all disappear, right?
I'm going to ask you and Soyeon Yi, two speakers, and the KASSTA officers to stay for a minute until this Zoom end. We need to take a few more, minutes there. Yeah.
Okay.
So and the KSEA, Katie, please stay for a minute. Yeah. So, and with that, I would say officially we should close now and wrap up this meeting. And for this fantastic speakers, we hope to have another opportunity for you to be able to interact, so don't take it like as if this is the last opportunity. So more questions you may have, but you can use it for the next.
Okay. Anyway, yeah, my thanks to the speakers and organizers.
Fantastic speaker today for the excellent job.
Okay, thank you.
Thank you.
Your exit comment in the chat. We will take it. Oh yeah, another thing. I will post the link again. Sign up for KASSTA to join KASSTA so that you can get future meeting notifications. Yeah. All right, thank you everyone. Wonderful. So you can now stop recording so that you can go into our private discussion.